So for the final talk, we have Dave Morrison from UCSB, and he'll tell us about codimension 7 revisited. Please, Dave.
So I apologize for the technical. Is still.
There's something wrong with your sound.
You're dropping out.
Yes, I. First thing I was going to say was that periodically I will drop out. Okay, I think it's back. So periodically I may drop out, and I apologize. I will try to keep track of that and just pause a little bit. This is a much more elementary talk than the discussion we've just had, and it's more aimed at mathematicians. It would have been great if we'd been able to do it ahead of time, but I do apologize about the technical problems. So if we want to construct four-dimensional effective theories, one natural way to do that is to compactify the higher dimensional physical theories that we know, the ones that include gravity and some quantum aspect, in particular M theory. And compactifying M theory on a 7-manifold is a natural way to get a four-dimensional. In fact, we could compactify M theory on any manifold of any dimension and get a lower dimensional theory. It's 3 + 1 dimensions that leads us to the choice of a 7-manifold. M theory is an 11-dimensional theory. So we want to get down to 4 dimensions, we use a 7-manifold, but we get other interesting physical theories in principle by compactifying M theory on other Riemannian manifolds. However, it's been known for a long time that there are flaws in this procedure because there are important physical aspects that we would hope to model, which we cannot model by compactifying M theory on a non-singular space. And so it was proposed some time ago to compactify M theory on singular spaces as well as non-singular spaces and try to understand what we get in that way. So I get messages that the speaker is not working, and then I pause. So we might have started with the classical version of M theory, which is 11-dimensional supergravity theory that requires knowing a metric in 11 dimensions. It requires knowing a 3-form in 11 dimensions, and then one imposes equations called equations of motion in order to get a decent effective theory. One of those equations is to have a covariantly constant spinor field, because one of the fields in the theory is a spinor. Sorry, I mentioned the bosonic fields only, the 3-form and the metric. Other equations involve model, which is often used time to be a product of a compact space and a non-compact space, and put the time in the non-compact space so that the ultimate physical theory will end up in the non-compact space. And doing that makes sense using what's called the Kaluza-Klein mechanism. I'm going to take the various fields in the theory, consider the components in the compact direction, consider, for example, the Laplace operator operating on metrics or differential forms or functions or whatever, expand in terms of eigenspaces of those guys, and get an effective theory in that way. That process is called compactification, or is closely related to dimensional. As I mentioned, there are a couple of particular features that one would want in a 4-dimensional theory, particularly non-abelian gauge symmetry, which cannot be realized using compactification on a manifold. So we allow certain kinds of singularities. This is a collaboration on special holonomy, But the main reason that the special holonomy cases are interesting in physics is that there's a covariantly constant spinor for these special holonomy spaces. And it's that covariantly constant spinor which leads to supersymmetry in lower dimensional theory, which is the important feature from the physics point of view. Okay, so to get non-abelian engaged fields, actually Simon asked this in an earlier discussion, well-studied based on ADE type singularities, might be called ALE spaces as well. Those are spaces, those are types of singularities which could occur in real codimension 4. There are other cases, real codimensions 6 and 7, if I'm compactifying to 4 dimensions, and real codimension 8 for compactification to 3 dimensions. The 6 wasn't really mentioned, for example, in Laura's slide a few minutes ago, because we know that codimension 6 is not going to contribute interesting physical effects for the models that we care about. But if we want to do a complete mathematical study of this whole program, we should consider codimension 6 as well. So particularly in the codimension 6, too much, and that's been to the program of finding compact examples. Now, we just heard that a lot of lessons about the physics can be learned from a non-compact example, but ultimately it would be ideal to have compact examples so that we would have a complete gravitational theory. Might even be nice to know what all the compact examples were so that we could maybe integrate over the space of all such theories and hope to zoom in on properties of the world around us by this kind of study. So one of my key points, I would say, is that I want to make sure that we have the ability, if possible, to get a compact space. So we're in an incomplete situation. Again, on Sakura's slide, there was the specify the codimension 7 singularities. I'll come back to that in a moment, but I'm going to write down some kind of framework, which I hope is reasonable mathematically. For example, framework, I could find all of the singularities which were at finite distance from the bulk of the moduli space in a Weil-Petersson type of metric, or maybe a Gromov-Hausdorff analysis. I might hope that all of those would fall into this particular class, which is already known in the case of K3 surfaces. Okay, so I'll spend a few minutes talking about K3 surfaces and gauge fields, how we get gauge symmetry out of this setup. The first place that we're seeing a non-flat metric with a covariantly constant spinor is Ricci flat metrics on K3 surfaces. And the space of such metrics has now, or the Gromov-Hausdorff sense. And in those limit points, certain S2s, which existed away from the limit points, have shrunk to 0 area. It's known by some work of Kobayashi and Todorov, which generalized Yao's Calabi-Yau theorem, that the limit of nearby Ricci flat metrics is asymptotically orbifold metric on the limiting metric space. So it's a limiting metric space in the sense of Gromov and Hausdorff. It has a metric on it which looks just like an orbifold metric near singular points. Those singular points are isolated. And if we look at the M theory compactified on a non-singular K3, which is close to one of those limit points, then there is a 7-dimensional gauge field in the spectrum in that spheres mechanism in which the gauge field is on those shrinking 2 spheres. So there's an overall setup in which you would consider both singular and non-singular spaces. You would consider a gauge, sorry, I think I put it on the next slide. You consider a gauge theory in which you had, it's really only a 7-dimensional gauge theory because of where these things are localized. You would have massive gauge bosons in those theories, but the masses would be parameters, and you could tune those parameters to 0. And you couple this, you compactify the coupled theory in such a way that the masses of the gauge bosons match up with the areas of the shrinking two spheres. So that's a really nice setup for understanding how gauge. If you don't include those gauge fields, you get an incomplete physical theory. I think that's a lesson that we learned long ago in physics. One thing I'd like to point out, which is kind of remarkable, this real codimension 4 behavior, which we're identifying by physical effects, is exactly the mathematical behavior that you would obtain in a non-collapsed Gromov-Hausdorff limit in real codimension 4. With various hypotheses, that's work of Cheeger, Tian, and Neighbor. So we have a really satisfying matching of a certain class of singularities in real codimension 4, an associated gauge field that you need to put in to complete the discussion of the physical theory. And then that physical theory includes massive gauge bosons on nearby non-singular K3 surfaces, things which were not part of the supergravity approximation, the things that came from M theory directly, part of it. Okay, I'd kind of like to repeat that. Oh, sorry. I'd phrase things in terms of compact K3 surfaces, but I don't really need the surface to be compact. The final step, I'm actually compactifying, but before that, I might take, in the compactification scheme, instead of taking arbitrary forms and functions on the space, I might take ones which die off at infinity in appropriate ways, and then I could still talk about the reduced theory in the non-compact case. And the essential thing about this construction is how to couple the effect of those shrinking two spheres through a gauge field to the rest of the theory. And that business can be done using, for example, Cronheimer's construction and ALE spaces that you might now consistent about whether I call them spaces. Well, we've heard a lot of discussion about that. There are lots of technical issues with respect to setting that up appropriately. Higgs bundles, spectral covers. We've so far had to proceed dimension by dimension, or I might say geometric structure on the space of ALE singularities by geometric structure. So whether it's Kähler or not, for example. That part of the story is something that is being actively worked on, and I think is being understood pretty well. So one aspect of that story is, again, I'm describing a coupled theory in which I've got the lower dimensional gauge field interacting with the supergravity theory. There will be equations of motion with that reduced theory. Those equations of motion come from knowing what these interactions are. They're differential equations on the ingredients of the theory, and they include Ricci flatness of the metric, which is the Einstein, as well as covariant constancy of an appropriate spinor field, and equations that belong to the gauge field itself, and those should all be imposed. And again, that's, I think, what gives a slightly different character to various dimensions of attempting to do this, but there's a standard background for all possible dimensions. One possible complication, which has come up a number of times at this meeting in the context of the work of Joyce and Karagiannis, is the possibility that the singularities could be resolved locally, but there might be some global obstructions to doing the resolution. I speak of singularity resolution. In this K3 case, there's not a clear distinction to get to a smooth space. In any event, there can be, for example, unexpected zeros in one forms, which would cause you to not be able to resolve. And that's something that has to be dealt with in the general situation. Okay, so I now want to come to the next case, which is Calabi-Yau threefolds. Sakura, I have no idea what time I started, so I don't know how long I've taken.
So I think you started about 10 past, maybe a little after that. So you have
Okay.
10 minutes left, 12
Yep.
minutes.
So the next case in which we have some covariantly constant spinors occurring is the case of Calabi-Yau threefolds. And in both this case and the K3 surface case, the analysis is because properties of spaces, properties that could be particular cohomological properties of the Kähler class. On the other hand, we don't have as much information in the Calabi-Yau threefold case. In the K3 case, the metric was hyperkähler, and the structure of the moduli was governed a lot by the periods of the two forms related to that hyperkähler structure. And that was enough, for example, to get the asymptotically orbifold metrics in the limit that we wanted. But in the Calabi-Yau case, we know much less, excuse me, we know much less about the metrics. One thing we do know, thanks to work of Hayakawa and Wang, is which algebrogeometric singularities might occur at finite distance from the bulk of the moduli space. And again, the distance is being measured sense, and it's probably also correct in the Gromov-Hausdorff sense, but I don't think that's been checked. The real codimension 4 singularities are exactly the same, but there are some new ones which are real codimension 6, and they might be isolated real codimension 6, or they might be worsening of a codimension 4 locus. So it's important that both cases are considered. And we don't know much about the metric behavior in this case. I want to point out that the simplest such singularities, which are so-called conifold singularities, they admit a cone-type Ricci-flat metric. It was written down a long time ago by Candelas and De La Osa in the physics literature, and later by Stenzel in the math literature, independently, I believe. And this may be one factor which has influenced people to assume that they want to study cone on. It's been known for quite a while that, for example, for singularities of this form, x squared plus y squared plus z squared plus t to the k equals 0, with k bigger than 2, they typically don't have conical metrics. So the non-existence of cone metrics for k at least 3 was shown by Gauntlet, Martelli, Sparks, and Yau a number of years ago, a couple decades ago, actually. And the existence of non-cone metrics for k at least 4 was announced by Hein and Nadel and proved by a number of people within the last 5 years or so. The k equal 2 case is the conifold case, and the k equal 3 case is still partially open, according to the statements that I've just made. So here's the case where we know there is a good Ricci-flat metric, but it's sort of a cone. For singularities of this type, these codimension 6 singularities, is capture the physics content by adding what are now going to be 5-dimensional fields. Before I had 7-dimensional gauge fields because that's where the singular point was located. It's localized onto that singularity. Now I'll take 5-dimensional fields. They're scalar fields instead of gauge fields this time, and they correspond to the shrinking S2s, which might be shrinking as you approached the singular space from a nearby Crepant resolution of singularities. And again, wrapping M2 branes on shrinking S2s is what is responsible for massive fields. They're not gauge fields this time, they're scalars. They're massive fields which become massless in the singular limit. By the way, the fact that I'm keeping the covariantly constant spinor at all times means that although I'm comes in a multiplet, there are fermions which go along with the bosonic components of the fields. All of that has to be taken into account to write a complete version of the story. However, the threefolds fails to be complete in two different ways. First, there are interesting cases, and we heard a talk about that this week, where a divisor shrinks to a point instead of a curve shrinking to a point. Divisor and curve I'm using in the complex sense on my Calabi-Yau threefold. And then I get a conformal field theory, and what I get is much more complicated. Second issue is that not every canonical threefold singularity admits a Crepin resolution. Sometimes you have to deal with some residual singularities if you want to retain crepancy, so retain triviality of the canonical bundle and have a hope of having a covariant and constant spinner. You might have to deal with some residual singularities. Among examples of those is the k=3 case I had above, the one where we don't know what the metric is. So I would say that's a really interesting small problem to understand metrically what's happening for the x squared plus y squared plus z squared plus t cubed equals 0 singularity. There's been recent studies by Grassi and Wiegand in physics, of the physics of those Q factorial singularities. So my expectation is that we will have descriptions probably as rich as the description we have in the ALE cases for all of these cases in the near future. In any event, we should do the same thing we did a minute ago and introduce 5 when this as 11-dimensional and the 5-dimensional map to oppose equations of motion. We have to allow things to vary, and we have to worry about things analogous to those zeros in one forms that were encountered by Joyce and Karajanis. However, all of these things can be described ultimately in terms of the algebraic geometry description of these singularities, and then hopefully one matches the metric geometry to the algebraic geometry. Okay, in my last couple of minutes, I'm going to describe the case of holonomy G2. I think in my abstract, I also mentioned spin 7, but I don't really have time for spin 7. We are on even shakier ground in terms of understanding the metric and the metric near singularities. And one of the things I really want to emphasize in this talk is that although examples in which the metric has a conical form, that there's no reason to assume that that's always true. No reason I can see to assume it's always true. Metrics in the Calabi-Yau threefold case suggests that it probably is not true. So it'd be interesting to have explicit examples of singular G2 spaces that have non-conical metrics, just like the Hein-Nodal results gave us singular Calabi-Yau threefolds with isolated singularities and non-conical metrics. It would also be great to have a classification of such singularities, to have a classification of the effective physics associated to them. Presumably, we'll be trying to model that effective physics by 4-dimensional physical fields instead of the 5 or the 7-dimensional fields. And then in some grand scheme, put everything together, couple a 11-dimensional supergravity, 7-dimensional gauge fields, 5-dimensional and 4-dimensional other fields, compactify that on one of these G2 spaces with a set of singularities, which hopefully by then we understand, and just calculate what the effective theory would be. That's a little ambitious right now, particularly since we don't even understand all the local models, but I would like to urge that we can still describe something like compact models, even with our limited understanding. Here's the basic structure I would propose for such a model. So what I'm going to do is delete small neighborhoods of all the singular points. If I delete small neighborhoods of the singular points, I'll set a 4-ball thing that I would want to remove set which is fibered over a one manifold and whose fibers look like neighborhoods of canonical threefold singularities, six-dimensional canonical threefold singularities. And similarly, I'd want to take out some small seven-dimensional neighborhoods of codimension 7 singularities. I don't know how the structure of the boundary is related to the interior exactly, but there's a fair amount about the physics which I can learn even from that deleted set. And I can learn that by looking at that boundary and by taking integrals of appropriate differential forms, whether they be from the supergravity theory or from these auxiliary fields and forms that we may have introduced in modeling the physics near the points. This is, this is a type of the approach used by Witten to measure chirality for the new physical fields created by the singularities of codimension. That many relevant physical features, for example, charges are often measured this way, and other physical features could be measured this way. So it says our understanding is quite unsatisfactory. However, we can build some kind of general framework which has a chance of capturing all the phenomena we need. And we hope that building such a framework, I didn't give a lot of details in this talk, but I gave an outline of the framework, and we can hope that having such frameworks will lead to further progress in constructing both local and global examples and understanding the physics that we generate in that way. I'll stop here.
Okay, thank you very much. Are there any questions?
Yeah, could I make a comment?
Yep.
So it seems to me that you can probably at least conjecture a kind of ansatz or what your metrics near singularities look like, which might be detailed enough to do physics with. And that's that it's a reasonable expectation that even if your singular metrics are not modeled on a cone with an isolated singularity, it should still have a tangent cone,
Right.
you know, by kind of geometric theory, geometric measure theory type considerations. So you should expect a tangent cone which may have singularities itself. So for a G2 manifold, you want a tangent cone which could, the kinds of singularities a tangent cone could have would be codimension 4 orbifold singularities, or possibly codimension 6 kind of Glaby-Yau cone type singularities. And so your first approximation to your manifold is the thing looks like the cone. But then your second approximation is that as you move away from the isolated singularity in the direction of a singularity in the cone, that that singularity gets resolved but at a much smaller length scale than is happening on the cone. So, for example, you might expect to see, imagine having a G2 cone with an isolated singularity at the origin plus codimension 4 orbifold singularities. And then you can imagine moving off in the orbifold singularities directions and desingularizing those using some collection of harmonic one forms on the orbifold stratum, because somehow the size of the desingularization might be order r squared rather than order r, so that it doesn't contribute to the tangent cone.
Right. So I like your picture quite a bit, but let me point out something about this class of club. X squared plus y squared plus z squared plus t to the k equals 0. Mm-hmm. So the tangent cone, I mean, we know a Zariski tangent cone, and that's in that situation, and it matches with what happens metrically. So there is a region sort of very near the singular point where it kind of looks like x squared plus y squared plus z squared equals 0, not an isolated singularity. And then the t to the k comes in at some other level of approximation. So I completely agree, although I'm not sure that the phenomenon you described of singularities, codimension 4 singularities, is going to be the only cause of such higher order behavior. So that's
Sorry,
We
lost
can't
you.
hear you, Dave. I think the last bit got lost.
For K=3, I'm not really sure, and my hope is actually that if one understood that better, one might get someplace with this general program. But I completely agree that building up something that's not quite a metric cone, but is approximated by one, and then has a better approximation by something with a correction term, and maybe a better approximation by something with a further correction term, and so on, that is a reasonable way to go.
Great. Any other questions? I think we've also, is there an urgent question? Then please go ahead. If not, we should close the session now and actually the workshop. I will hand back to perhaps Miriam for some final words.
First of all, I want to say I'd like to thank my organizers, both to Bobby and to Jason, that, you know, with the United Front, I think we managed to coordinate that. Also being rather new at running online meetings. So I'm personally quite happy that things went relatively smoothly and that we hopefully have all the talks recorded properly so anyone can see them later. I'd like to thank all the participants. Of course, it was extremely the quality of talks and communications between math and physics community, right, that somehow is building slowly but surely through this communication. So thank you, everybody.
Thank you. And we'll see each other at AIM, I think, for the next meeting, again virtually.
Thank you. And I think this is it.
Right.
Bye.
Bye.